Okay, hi everyone. So last time we discussed how we can partition a set of points using the zero set of a polynomial. As promised, today we'll talk about how to reduce to the case, if possible, where almost everything clusters on the zero set of the polynomial. So let's remember the setup. We have a bunch of points, finitely many points in a set S in Rn. So it's important that it's Euclidean space that live inside lines, L lines in Rn, and we want to count them using polynomial partitioning. The first step is to choose a degree. Sorry, I should have said what the goal is. So let's say that we want to show that our number of points is at most a function of the number of lines. And for instance, we'll apply this to the case where we have this general desired estimate. The number of points is at most a constant, C bar, times the number of lines to a power p. Okay, so we choose a degree to partition with. It should be a quantity that's at least 1, so that we can play the role of the degree of a polynomial. And in fact, you don't even have to choose it from the start. You can run the process with an arbitrary degree, and in the end, fix your degree according to what you want. Okay, and then you find there exists a polynomial of at most that degree, whose zero set partitions the set of points as in this picture. So we know how many cells we have, and we know at most how many points we have in each cell. So the number of cells is fully determined, remember, by the degree of the polynomial and the dimension, and each contributes at most the average number of points. And as we said, we have two cases, the cellular and the algebraic case. The cellular case is when, say, more than 50% of our points live inside the cells, so avoid the zero set. And the algebraic case is the one we eventually want to reduce to here, where more than 50% of the points actually live on the zero set. So that big proportion is clustering there. The goal is to somehow get rid of the cellular case to get to the algebraic one. We need that because the algebraic case represents some extremal examples in principle, so we cannot really avoid it, but we want to reduce them. And it's quite standardized how to deal with a cellular case. So in principle, you either show it's impossible or you deal with it by induction, say, on the number of lines. So induction doesn't always work, but if it does, that's great. When I say that the cellular case will be impossible, I mean that the degree that we will choose eventually, that we will run this with, will be so big, not too big, but so big that it will engulf most of our points. The variety will have enough complexity to engulf most of our points, and therefore the points won't be clustering inside the cells. Okay, so let's see how we work in the cellular case. So let's say we're here, more than 50% of the points live in the cells, and always we work in a typical cell. What do we mean by typical? We mean a cell of very average behavior. So we will know how many points are in the cell pretty much, and how many lines pretty much intersect the cell. So here is the numerology that we will eventually explain that a typical cell enjoys. So the average cell, a cell of average behavior, we'll see what that means, contributes about the average number of points. Not at most the average, also about the average. So pretty much it's fair share. So the average cell will have this property. That's a very simple counting estimate. And more interestingly, the average cell will be intersected by very few lines in our family. So at most the original number of lines over the degree to the n minus 1. So degree to the n is the number of cells. This new denominator for the lines is a bit smaller. This is interesting because it has to do with how lines interact with this zero set. But in any case, it always holds. And then we will pick a cell that satisfies both. In every cellular case, there will be a cell that satisfies both these things. And then the idea is that you only work in that one. So that is a typical cell. And you do everything you want just through that one cell. This intuitively, I guess, means that every cell is not very different from every other cell. So we cannot really distinguish between the cells as some being important and as some being less important. In the cellular case, where they contain most of the points, in principle, they are indistinguishable, and just working in one should give you what you want. Okay, so let's see what we have in it, in this typical cell. We know how many points we have. Let's say S cell is the set of points that live in our cell. And we know how many lines at most cross through here, enter this cell. So L cell, let's say, is the set of lines in L that enter this cell. Okay, we know we know estimates for these things. We know that the number of points in the cell is about the average, and we know that the number of lines in the cell, so by this I denote the number of lines in the cell, is at most, again, a kind of average that we'll see in a bit. So why is this useful? It's useful because, remember, we started with a very big picture here, where we had many points and many lines through those points. And now we've zoomed in a much smaller picture with fewer points and fewer lines through them. So maybe we can work by induction. That's one idea here. For instance, if you know that your degree is bigger than some big constant, then this upper bound of the number of lines in the cell is smaller than the number of lines. The number of lines in this typical cell, the number of lines that cross this typical cell, is strictly smaller than the total. So maybe you can do induction on the number of lines. Okay. I'd like to explain the two ways now, the general strategy with which the cellular case can be dealt with. So we are in a typical cell now. We know the numerology for points and lines in that cell. And there are two ways to proceed. Okay. So one, as we said, is to do induction on the number of lines in that cell. So work in the cell by induction on number of lines. So we can apply an estimate, an inductive hypothesis in the cell perhaps. And the other, the second way, is to just apply a known estimate. If the induction doesn't close, we should do something else. And another thing we can do is apply a true estimate, a known point line incidence estimate in the cell. In other words, for the points that live in that cell, which of course incident to the lines crossing that cell. Okay. So we'll see how each case can help. So let's begin with the induction one. Remember, the goal was to show that the number of points is at most a constant C bar times the number of lines to the P for some power P. Okay. So let's see how the induction could close, or if it always closes anyway. Okay. So, can you hear me well? Someone says that there is a continuing noise. Oh, okay. All right. So we can assume, I hope, that the estimate we want holds for one line, otherwise we're in trouble. So now that we have a general estimate we want to show for L lines, we may assume it holds for fewer lines. Okay. So so here we have the points in the cell, and we have the lines through them. They are exactly the lines in L cell, the lines that cross the cell. No more lines than those that cross the cell can actually interfere with those points. And we may assume by induction that the number of points in the cell satisfies, so the point satisfied this estimate. That this is at most the inductive constant times the number of lines through the cell to the p. Okay. And now we have bounds for these quantities, number of lines, number of points, and we replace them here. So this means that the left-hand side, which is about the average, is at most, and I'm putting a wiggle here because I lost something through the number of points. It's not exactly the average, it's a constant times that. So at most the constant I wanted times the number of lines, that's L over degree to the n minus 1, and all of that to the p. Okay. And now I rearrange to see what it gives me. So it gives me that the number of points is at most a constant I don't know, it could be quite big, times the constant I wanted, times L to the p, times 1 over, I collect the exponents for the degree, d to the p times n minus 1 minus n here. And you see that if this exponent is positive, then I have a sort of large denominator for appropriately large degree that will counteract this bad constant here and will close the induction. So if this p times n minus 1 minus n is positive, if the parent denominator is positive, equivalently p is bigger than n over n minus 1. This is an exponent we've seen for joints, for example. Then we can close the induction. Assuming that we have picked degree bigger than some large constant. Just the degree of large constant works. It will be divided by this constant hiding here, and it will make it disappear. So as long as the degree is equal to some large constant. So under this assumption that the exponent we are aiming for is bigger than this sort of magical critical exponent, however you want to remember, strictly bigger though, then the induction can close just by partitioning with a zero set of constant degree, so independent of the number of lines or points we have in our picture. And this is a very strong thing that you can forget now this case, the cellular case, and assume that your points are lying on a constant degree variety. That's very small degree. So that is good in that sense, but it only works if the exponent satisfies this condition. Now this exact n over n minus 1, it appears a lot in analysis, in the Kakeya conjectures, in the restriction conjectures. And usually in analysis, we don't care that much about sharp exponents, I guess. So, well, about sharp things. So this gives epsilon loss, I want to say. If you are aiming for a decent point exponent, you can't do it by induction. But if you add an epsilon to it, it becomes bigger than this threshold, and you can do this induction with a constant degree. So it works a lot in analysis, where we don't mind the epsilon losses so much. So you'll see more about that next week, I'm sure. But we may have situations where we don't have this condition for the exponent, so we want to do something else. And here is the other possibility, to apply a known point line incidence estimate in that cell. So again, you have your points here, you know how many they are. You know they are incident to the lines crossing that cell, for sure. So you could apply a point line incidence estimate there. We'll see an example later. And the point is, how do you work from there? This gives a relationship between these two quantities, points in the cell and lines in the cell. But those are related to the original points, the original lines, and the degree. So this will give a relationship between the degree and the original number of points and the original number of lines. So if we are in the cellular case, indeed, the degree should satisfy this relation relative to the other two quantities. So if we have picked at the beginning a degree that doesn't satisfy this relationship, then we get a contradiction here, and we could not have been in the cellular case to begin with. So this is the idea here. We get, this contradicts the cellular case if we have picked degree from the beginning that doesn't satisfy this relation. So that's how you work to get a situation where you don't have the cellular case at all. You pick usually a large enough degree so that this relation is not satisfied that you would get here. And once you get from this case that you have the relation, it must have been a contradiction, and the cellular case doesn't happen at all. So you reduce to the case where everything clusters on the zero set. So this is the general strategy. These are the two possible cases, and we'll see examples. Before that, I'd just like to discuss a little the numerology for the average cell. So we said that the average cell in the cellular case should contain about the average number of points. So why is that? So that is just a simple argument, counting argument. All cells contribute at most the average. So if many cells contributed a tiny amount to the points, then together they wouldn't add up to more than 50% of the points. The precise statement, because we sort of need it, is that more than 10%, say, of the cells contain each, say, at least 1% of the average number of points. So I will not do the proof because I think we will collectively fall asleep if I do, but the point is that you split the cells in the ones that contribute very little, so less than 1% of the average points. And this contribution is tiny in total. So the contribution of these is tiny. So you must have the big contribution, more than 50%, more than 49% or something of the points from the rest. The cells that contribute at least 1% of the points, of the average of the points. And this will mean, if you think about it for a moment, that these cells should be many. Okay. So more than 10%, let's remember that, have this good property. The more interesting property is the one about the lines, because it has to do with the zero set. So here's how you show this, that the average cell has this, is intersected by a few lines. So you notice that every line, not even in your family L, every line L enters very few cells, at most the degree +1 cells. So why is this? Let's draw a line. Okay, L. Here it enters this cell, then it goes into this one, it goes into this one, it goes into this one, etc. And we see from the picture that whenever it goes from one cell to the next, in the middle it must have crossed the zero set somewhere. So it crosses the zero set a lot. So why is this? Remember that the cells were defined by certain collections of signs of certain polynomials. So if you change cell, if you go from one cell to the next, then one of those polynomials must have changed sign. So by the intermediate value theorem, in the middle, it must have been zero somewhere. So you must hit the zero set. Okay, so this is it. If L entered more, so at least D +2 cells, every time it goes from one to the next, it would hit the zero set. So it would hit the zero set at least D +1 times. So more than the degree of the polynomial. The polynomial would vanish along the line more times than its degree, and we know that this would mean that L would be contained in the zero set, fully contained in the zero set. And then it enters zero cells. Enters zero cells. That's a contradiction. A line cannot enter at least d plus 2 cells and 0 cells at the same time. Okay, so this is general property for every line in the picture. And from this, you get that the lines in your family don't enter too many cells in total, and therefore the average cell must be intersected by few lines. So the average cell, and we'll write out what we mean, is intersected by few lines. And this is just a double counting argument. So you want to look at the average behavior of a cell. So you add the overall cells, the number you want, the number of lines that enter the cell. Okay. And you just you count in another way. You add the overall lines. This is the same as adding overall lines in your family. The number of cells that the line enters. And we have a bound for this quantity here from above. So this is at most the number of lines times the cells that a line can enter, which is d plus 1. So in total, we get at most twice L times D. Okay, and here you can sort of see where we're going. The cells, how many are they? They're about D to the N. So the average cell should be intersected in principle by at most this over D to the N. And you get exactly L over D to the N plus 1. The exact statement is this. Or one of the exact statements. More than 99% of the cells are intersected by very few lines, by at most this average. So at most a big constant, this can be big, times the all lines divided by d to the n minus 1. So 1,000,000 times the average. And you can work out these numbers. Okay, so this is where this numerology of the typical cell comes from. And let's remember, we said we have to pick a cell that satisfies both things. And we can, because the first property is satisfied by more than 10% of the cells. The second property is satisfied by more than 99% of the cells. So we can find one that satisfies both. In fact, we can find many. And then we get one, and we either work by induction or we apply a known estimate. And we hope that we'll get rid of the cellular case in one of the two ways. Okay. So let's do examples for this. So we said what the joints are last time. So let's take a family of lines in R3. And let's say J of L is the set of joints that they form. Let me remind you what the joint is. So in R3, you look at the lines in your family through your point X, and you want to see if the lines through X span R3. If this happens, then X is a joint. So they shouldn't be coplanar here. And last time, what did we do? We proved the lemma that controls the number of joints that we're looking at according to the degree of a polynomial that vanishes there. So that for every J subset of the set of joints, if we can find a polynomial, non-zero polynomial, vanishing there, then we can control J by the degree. The number of joints in that set is at most the degree of that polynomial times the number of lines. And we use this in combination with Dvir's vanishing lemma to control all the joints. They were at most number of lines to the 3/2 in R3. And we said that if we are aiming for more refined estimates than this one, it doesn't look like we can do it with the vanishing lemma. So we need the polynomial partitioning for that. to reduce mainly the degree that we're using. Right, oops, sorry. So here we are, let's define JK. This would be the set of K-rich joints in this family. So these are the set of joints formed by L, such that about K lines in L pass through X. Okay. And by about, I mean at least K fewer than 2K. And the goal, as we said last time, is to show that the number of K-rich joints is at most L to the 3/2 over K to the 3/2. Okay. So I'd like to say why we care about this, because I don't like doing things that are unmotivated. But it relates to the Kakeya conjectures that we discussed the first day. So we said that every Kakeya set in Rn should have okay. So we have full Hausdorff and Minkowski dimensions. So the Hausdorff dimension should be n, and the Minkowski dimension should be n. Okay, the first would imply the second, of course. Okay, and my tablet is going a bit mad. I'm not touching it, and it's zooming in. So maybe, it zoomed out by itself as well. So maybe I could restart it for a moment. And okay, so I'll turn off my camera again because this is weird. I'm sorry. Let me restart. Actually, no, I'm not turning anything off. I'll just restart. Sorry about this. It's going a bit mad. Doesn't even turn off. Yeah. Sorry about this. Okay. Okay, apologies about this. So, right, we wanted to show the conjecture is that Kakeya sets have full Hausdorff dimension. And we only discussed the Minkowski dimension part. Okay. So we said that there is another conjecture about delta cubes that are delta separated that would show that the Minkowski dimension is full. And this is this one. So for every delta positive, we take any family of delta separated delta cubes, and we want to show that their union behaves as if the cubes are disjoint. So we want to show that the union is comparable in size to the sum of the sizes. Okay. And this would imply the Minkowski dimension is full. We didn't discuss the Hausdorff dimension though. So there is another conjecture that's stronger than this one that would imply the Hausdorff dimension bound. And this is the maximal Kakeya maximal operator conjecture. So it starts again with a family of delta separated delta cubes. However, it says something else. It says mainly that because we want their union to be very big, their overlap should be very small. This is what it describes, small overlap. So what it says is that for every point, you look at the number of cubes in your family through the point, and you want to show that this behaves pretty much, on average, like a constant, so that you have very few cubes passing through its point in principle. A way to quantify this would be, say that if you raise this quantity to a large power, this behaves pretty much the same way as if you raise the quantity to the power 1. This would mean that the quantity is about a constant. And you want this to be true on average, so you integrate over x. This is what the conjecture says. And the right-hand side is very explicit. It is the integral of the sum of the indicator functions, characteristic functions of the cubes. And you can pull out the sum, so it becomes the sum of the sizes of the cubes again. So, of course, notice that it's over the union of the cubes that we consider the integral. That's only where the points can be assigned this kind of weight, this kind of multiplicity, otherwise it's 0. So it says that whether you're counting your points with multiplicity, with a weight or not, it's pretty much the same thing. And if you apply it in 3 dimensions, the n over n minus 1 just becomes 3/2. This is what you want, and notice that the right-hand side, if everything is correct, then the Kakeya conjecture is just the size of the union. In any case, it is definitely as large as the union can get, the largest the union can get. Okay. And we will prove instead that for every family set L of lines in R3, not for cubes, but for lines, the K-rich joints are at most number of lines to the 3/2 over K to the 3/2. And if we rearrange, we start saying something very, very similar to the above. This would be true for every dyadic K. Okay, that's what we want to show. So it would mean that JK times K to the 3/2 is at most the number of lines to the 3/2 overall dyadic K. I add up overall dyadic K, and I'm getting a log loss, log of L, because K is the number of lines through the point. They can't be more than the number of lines, so they're at most log L, the dyadic ones. And notice here, these are K-rich joints. So K is just the number of lines through each joint. So this is the same as saying that if I add overall joints formed by L, the number of lines through X, of lines through X to the 3/2, I'm getting at most up to log loss the number of lines to the 3/2, and the right-hand side is the maximum possible number of joints. This is largest size of the largest J row. So it is analogous to the continuous case. So it is something maybe interesting to try to prove anyway. And here we go. This is our goal. And we will apply polynomial partitioning to JK, to the k-rich joints. So, so we will partition with the zero set of a polynomial p non-zero of degree at most b. And this b will be determined in a bit. Okay. So we use such a polynomial of such degree. We have fixed our d, let's say, and then we get that the zero set splits R3 in about d to the 3 cells, each containing its fair share at most. At most, the number of points over d to the 3 joints in JK. Okay, that's what partitioning says. And we have the cellular case, where more than 50% of the points in JK live in the cells. And we have the algebraic case, where more than 50% live in the zero set. We want to reduce to this, and hopefully by the end we will have fixed degree that's considerably smaller than the one coming from Dvir's vanishing lemma, to get something more interesting. So as soon as notice we reduce to the algebraic case, immediately we will know that our joints in JK, where the polynomial vanishes, or on the majority of which the polynomial vanishes, are at most the number of lines times that degree. So we will get some bound. All right, so as we said, we want to deal with the cellular case. Here it is. We pick a typical cell, and we have a numerology we understand in there. The number of joints, k-rich joints in that cell, is about the average, and the number of the lines crossing the cell is at most the average. Okay, this is the numerology. And what we'll do is we'll try to do it by induction. So here is the estimate we want. Here we have the exponent 3/2, that's n over n minus 1. You should not expect this to work by induction already, but let's just say it. So this is something that holds for one line. So we assume it holds for fewer lines than the L we are working with right now. And therefore it should hold, the estimate should hold inside the cell. If the degree we pick is just bigger than some constant. Okay. So we may assume that the number of k-rich joints that live in the cell are at most the inductive constant times the number of lines in the cell to the 3/2 over k to the 3/2. The reason is that the joints in my cell only lie in lines in L cell, right? So I see about k of them through each joint. Okay, now I go and replace my quantities, my bounds from above. Well, the left-hand side is about jk over d to the 3 up to a constant multiplicative factor. So I get this is at most a constant times the inductive constant times L over d squared, that's an upper bound for L cell, to 3/2 over k to the 3/2. And now I rearrange so that I start seeing the estimate I wanted. Jk is on the left. It's at most a constant I don't understand, times the inductive constant times L to the 3/2 over k to the 3/2. That's good. And then the d to the 3 from the left will come up here over whatever comes from here. That's d squared to the 3/2. And you see that they cancel out entirely, which means I'm not done because there is nothing to destroy this constant I accumulated through my refinements. So the induction doesn't close. And it's not a surprise, it's the problem of this exponent, the 3/2. So let's just try to finish by induction, but for a slightly weaker estimate, as I said, epsilon losses work by induction, just beyond the critical exponent. So let's aim for this one. It holds for one line. we partition, we work in a typical cell which has this numerology, and we may assume that by inductive hypothesis, we have this thing holding. And of course, okay, also the constant should depend on epsilon, otherwise it doesn't make sense. Okay. So below, I just have the constant C epsilon, but I have plus epsilons here, even with the bounds. And now the d to the 3 from here will stay as it was, nothing changes. I'll have a plus epsilon, but for the denominator, I have 3/2 plus epsilon, equals a 3. Which means that I will have a d to the 2 epsilon left. So get that jk is at most a constant times the inductive constant times the stuff I wanted, that's good, times 1 over d to the 2 epsilon. And this is just enough to help me close the induction. If I just pick d, so that this denominator destroys whatever constants hiding here. So we're done in the cellular case for d equal to large constant, independent of the number of lines, number of points. And we can thus get rid of that, it's dealt with, and reduce to the case where everything clusters on such a degree variety. I will not do the algebraic case here because I was aiming for something better. I was not aiming for the losses with the epsilon, I was aiming for something better, so I'll deal with that for the better estimate. So I have a new goal to do this without the loss, and here induction in the cells won't work. You've seen that. So instead, we'll go to a typical cell and we'll apply a known estimate, something that actually holds. And the tool will be, the estimate we will apply, will be the Marina-Iliopoulou theorem. So this is the theorem that holds in all dimensions, 2 in particular, and extends to all. It says that for any set L of the lines in Rn, we can control the k-rich points. So for every k at least 2, so when at least 2 lines meet at points, the k-rich points can be controlled by the number of lines and the level of richness, k. But if the richness is small, then we get a very interesting estimate. If the richness is large, we won't be getting such an interesting estimate. Okay, so the interest in the Marina-Iliopoulou theorem is the low richness case. It gives this bound for the k-rich points, and the interest of it comes from the fact that instead of a 2 here in the denominator, we have a 3. With a 2, it would have been trivial. Okay, and we have L over K, a much simpler thing for high richness. The high richness case in R3, you can imagine it as bushes, independent bushes of K lines meeting. So this is a situation where you have this second bound. Okay, in any case, let's just see what this means for our joints. For the K-rich joints, because they're K-rich, according to the level of richness, we do get an estimate. So for low level of richness, we're getting this, which is not trivial. And for high levels of richness, we're getting this. And notice that in this high richness case, we have immediately the estimate we were aiming for. We have something better. This is at most L over K to the 3/2. So we are done, and we don't need to care about it. We may assume that we are in the low richness case, and the joints satisfy this nice bound. So what is interesting about this? It gives me a quantity that is bigger than 1, and that's highly non-trivial that it's bigger than 1. So if I rearrange, I get the right-hand side over the left-hand side bigger than 1. And I'll use that degree, actually. So this is a degree that's very interesting because it depends on everything, like the points I have, the lines I have, the richness. And that's the degree I will use. It will follow from the proof that I should be using that degree, but I'm telling you in advance. It comes from some Erdös. So here's my new goal. I will partition again, and I'm saying already that the degree I will use is this. And of course, like before, I have d to the 3 cells, each contributing at most its fair share of points. I have 2 cases, the cellular and the algebraic, and my goal was to get rid of the cellular one. Like before, we have many points there. We know the numerology of the cell, how many points and how many lines intersected. And now we will apply some Erdös for the points and lines in that cell. So here are the points and lines. The points are k-rich. The points in the cell, jk in the cell, are k-rich for the lines that intersect that cell. So we applied for the pair of k-rich joints and lines through the cell. And we get that for low richness, so the richness depends on the number of lines we're considering. So the numbers of lines in the cell only. So there is also the other more trivial high richness case, which is written on the other page. This should be an interesting situation here. I'm getting that the number of joints in the cell is at most the number of lines squared over k to the 3, richness to the 3. That's what it says. And now I'm going to replace these quantities with the bounds I have for the typical cell. The left-hand side is the average, and the right-hand side is at most the average number of lines squared over k to the 3. And I'll see, as I said, that I see a relationship here between my degree, my points, and my lines. So I'll rearrange and see what it means for the degree. It's d to the 4 on the denominator on the right, so it should be at most L squared over jk times k to the 3. So if I am in the cellular case indeed, it must have meant that the degree was at most a constant times this quantity. I will have picked a degree, just a bigger multiple of this, so that this is a contradiction. So this is contradiction if I have picked degree equal to say a plus 1 times this quantity. And this means that if I have gone from the beginning and I have partitioned with such a degree, so that's the constant hiding here, a plus 1, I got a contradiction in the cellular case. The cellular case can't have been true. So the points were not clustering in the cells, they're clustering on the 0 set. There is this high richness case that I didn't talk about. Let's do that quickly. That gives me, okay, that the cellular case could actually hold if I was in that case, but it gives me a much, much better estimate than what I'm aiming for. So the k-rich points in this case, in the cell, will be at most this boost situation. And now if I use my bounds, so this is the average, and here is the average for the lines, I'm getting that the joints are at most L over K times D. Now I have picked my degree, I know what it is, so I just replace it, and I see all these factors depending on my points and my lines appearing, and I just put JK here, and I notice that JK squared is at most L to the 3 over K squared, K to the 4. And now I lose the square, 3 halves, and the square here. And that's much better than what I was aiming for. The denominator is there. Okay, so that's how we deal with a cellular case. Much, much more work than with induction, but it works. And the algebra case now is where I wanted to get. most of my joints are clustering in the zero set. So from what we said last time, we must be able to control the number of these joints by the degree of the polynomial we chose. That's at most D times L. D, I know what it is. I replace it. It came from somewhere at the trotter. Times L. And now I rearrange. So JK goes here. So JK squared is at most L to the 3 over K to the 3. And then I divide with a half. And then I'm done. So you see that I did find a lower degree that got me where I wanted. Okay. So that's really what I want to explain about how you deal with a cellular case. And then the algebraic case, how it's dealt with, depends on the problem. But in the time we have left, I'd just like to go through a little tour of the paper by Guth and Katz, where polynomial partitioning was introduced, for a seemingly unrelated problem that actually turns out is a point line incidence problem in R3. And they actually attacked it using the numerology we already saw. So the Erdös asked this question. Let's take n points in R2, not in R3 here in this example. How many different distances do they determine? So say I could have a point, say, in the center of a circle and many other points around the perimeter. And you see that between this point and all others, as I have the same distance, of course, the radius. But you start saying more distances when you consider, say, this point. Its distance from the others as you go away in the perimeter starts to vary. So you expect to see many different distances. And I've drawn here a grid, a root n by root n lattice grid of integer points, because it feels like a lot of distances should be repeating here. So this should be a bad example. It doesn't look like it should be having a lot of distances. It looks like very self-similar. So how many different distances do we have here? If we take any distance between any 2 points here, it's at most diagonal. It's at most root n. So if I square it, I'm getting at most n. So the square of every distance is at most n, but also every distance can be written as a sum of 2 squares. Every distance squared is the sum of 2 squares. Okay, so it's the sum of 2 squares. So I'm just looking at the different numbers below n that can be written as a sum of 2 squares, and that is about n over root log n. So I have this many distinct distances here. And Erdös said that this should be the worst case, so always we should have at least this many distinct distances. And Guth and Katz effectively proved this. They showed that the distinct distances are at least n over log n. So this denominator is a bit bigger, so it's slightly worse lower bound, but effectively it's what we want. Okay. And the idea, as I said, is to transform this problem into one about incidences between points and lines in R3, so one dimension higher. And this existed already as a concept. This was the Ellenberg framework. So they said, we want to show that we have many different distances between these points. So we want to show that it is uncommon for distances to repeat. So here's the distance repeats. That's bad, but it should be uncommon. So the idea was that it is uncommon to get pairs whose distances are the same. Quadruples like this in our set, P1, P2, Q1, Q2, that satisfy this equality. And the uncommon can be quantified via Gijswijt. It's not hard. Okay. So let's study instances of this. What does it mean if a distance does repeat? Well, it means that there is a rigid motion that will take one line segment to the other. In particular, you can translate this one on the left, bring it here, and then you can rotate it up there. So there is a rigid motion that takes one to the other. And unless it's the degenerate case of a translation, which is a bit not so important for this problem, it will actually be a rotation around the point in R2. And I don't find that all that obvious. but actually it is a rotation. So if this is correct, it means that if I look at all rotations, taking P1 to Q1, and if I look at all rotations, taking P2 to Q2, then one of them should be both. And here I'm looking at all rotations, taking P1 to Q1, around, so some fixed point in R2. The fixed points should live in the perpendicular bisector. Now, if I look at all rotations that take P2 to Q2, the fixed points should live in that perpendicular bisector. So if I was correct that one rotation should be both, its fixed points should be exactly this, the intersection of the two bisectors. And you can actually check that because these distances are the same, the amount by which you rotate to go to do this movement is the same angle by which you need to rotate to do this. So it turns out that yes, there is a positively oriented rotation, which does exactly what I want. So let's look at the set of rotations that do these things. So the set of all rotations taking P1 to Q1, the set of all rotations taking P2 to Q2, these two sets should intersect somewhere. They should intersect at this single rigid motion or positively oriented rotation that does both. That, in other words, takes this length segment to that length segment. And now let's name these sets of rotations. R PQ would be the set of rotations that take P to Q, positively oriented. So I have translated the fact that the distance repeats into two sets having intersecting at a point. And then Ellenberg and realized that because every rotation in R2 can be determined by the fixed point and the angle of rotation, there are these parameters that parameterize all rotations. There is a way to do a change of variables in this universe of rotations and actually view every such set as a curve in R3. So that was what they noticed, that every set of rotations, like all rotations that take positively oriented, that take this to that, can be represented by some curve inside R3. And therefore, this information that these sets intersect at a point means simply that two curves, the corresponding curves, intersect inside R3. So every instance, in other words, of a repeated distance in my set in R2 can be translated as an incidence between these two curves, the corresponding two curves. So if I want to show that this is very uncommon, it's very uncommon for distances to repeat, I may as well show that it's very uncommon for these curves to meet in R3. So I want to control the incidences, point curve incidences for these curves. And that's how you change the problem to a point curve incidence problem. Now, Guth and Katz noticed that actually there exists a change of variables in the universe of rotations where these curves become lines. So it became much simpler. We just need to control incidences between lines in R3. And these lines didn't come out of nowhere. They were sets of rigid motions. So they have specific properties that not all lines necessarily have. And here is like a very big part of their paper and what they developed polynomial partitioning for. So you'll notice some similarities to the numerology we've been looking at. For any set of L lines in R3 that satisfies some conditions that these sets of rotations should. In particular, the condition was that there are not too many lines in any plane you choose inside R3. Okay. Under that condition, they controlled the K-rich points. Doesn't matter what this says, but notice the magical exponent again. It's 3/2. So they developed polynomial partitioning to deal with this problem, and they used the Sammaredi-Trotter degree because induction wouldn't work anyway. It's a 3/2, not 3/2 plus epsilon. And therefore, they partition with the same degree as we saw in this tight case, Sammaredi-Trotter degree. The cellular case runs through the same way that we saw. And then for the algebraic case, in other words, where the points cluster on a low degree, on that low degree of the variety, they saw that this vanishing property propagates to most of the lines, and then they started studying the singular points amongst their points, amongst the carriage points. They started studying the singular lines amongst their set. They could control them perhaps with Bezout's theorem. Then they looked at the second fundamental form of the points. You can control maybe lines along which the second fundamental form is 0, things like this. So that is tailored to the problem, but those are computational tools from algebraic geometry that you can use to deal with the 0 set according to your problem. And yeah, I think that's where I'll stop. Thank you very much. Maybe we can stop the recording as well.